All right, Chem 11. What I'm going to do is a number of problems off of the Quantitative Chem Review that is posted for you on your D2L page for the course. To do this review, you will need your Periodic Table-O-Matic 3000 Mendeleev edition and the Calculator-O-Matic 3000 solar-powered edition. So when the solar flares hit the Earth and it knocks down the power grid, who's still going to be able to do chemistry? This guy. All right, so I'm going to move these out of the way, use them off to the side. Got my whiteboard here. Obviously, I can't do all of the questions. That would take a really, really long time. So I'll try to hit on a little bit of everything for you here. All right, so we'll start off with number one. In number one, basically said you had 500 grams of calcium oxide. And it was asking how many molecules of calcium oxide would you have. All right. What you have to know for tomorrow is how to go from particles. Now remember, we don't ever use the word particles. Usually it's going to be atoms or molecules. In this problem, it would be molecules. But in terms of a general thing, we have to be able to do this. All right. So we got to go from particles to moles, moles to mass, mass back to moles, moles back to particles. You have to know how to do that. Absolutely must know how to do that. So with this one, we're starting with mass, grams, and it's looking for molecules, which is a type of particles. Although I will not use that word, again, particles, in any of my calculations. So I always start with what I'm given. And I have 500 grams, and I'm going to divide by the molar mass. That's where the periodic table comes in, and I will add the mass of carbon and oxygen together, and that's going to be 56.08 grams per mole. All right? I can just use a slash like that. It's the same thing as writing grams over moles. If you're typing this out tomorrow, use that. Just use a slash like that. It's quicker and easier. When I divide that out, I get 8.9 moles. That's not my answer. That just gets me to here. I went from mass to moles. I still have to go to particles, which is molecules. So I'm going to take this down here, begin my next step, this loop right here. And I'm going to say 8.9 moles times 6.02 times 10 to the 23 molecules per mole. Right? And when I do that, the moles will cancel when I multiply, one on top, one on bottom. Right, the same way grams cancel here. I multiply that out and I get 5.36 times 10 to the 24 molecules. All right. So that's number one, right? I'll do number two as well. Number two, I'll do in a different color. Number two is talking about lead 2 sulfide and how many moles of it you have if you have 7.2 times 10 to the 24 molecules. Again, we're using this, right? We're given a type of particle. The type of particle is a molecule. The other type of particle could be an atom. We're using molecules here, so we're right here. And it wants moles. So this is a one-step problem. So I take this and I divide it by Avogadro's number, 6.02 times 10 to the 23 molecules per mole. And when I divide that out, I end up with 11.96 moles. And that's what I was looking for, was moles. Now, it's important to make note of our exponents here. A few people messed up with the exponents, entering them into our calculators, right? And remember, a lot of the times you may have to enter this number with brackets around it like that. You don't have to write the brackets when you're doing the equation like this, but you might have to use brackets in your calculator. So this is our answer, just like that was our answer. So there's the answers to 1 and 2. Pause the video if you need to. I'm going to work on some more. I'm going to try to get a lot of this done in a short time. Like I said, I don't want to have like a 4-hour video. But 1 and 2 are done already. Let's do number 5. Number 5's got a little bit of everything in it. All right, number 5. With number 5, what you're looking for is chloride ions in 200 grams of lead 4 chloride. All right? So, let's take a look. Always write with what I'm starting with or what I'm given, 200 grams. So on that continuum, right, that was here a moment ago, I was at grams. I have to go to moles, and then molecules, because the grams here this grams, it refers to that. That's a molecule. It's not 200 grams of chlorine. So this one has 3 steps. We got to go from mass to moles to molecules and then to ions. So 1 calculation, 2 calculations, 3 separate calculations. So let's do the first step here, grams to moles, and we'll divide it by the molar mass of this molecule, 1 lead and 4 chlorines. When I add up those masses, I get 349 grams per mole. That will cancel out my grams. I'll be left with moles, and it ends up being 0.57 moles. I then take that 0.57 moles. I'm going to multiply it by, because I'm here now, sorry, moles here, I now got to get molecules. So, multiply it by Avogadro's number, 6.02 times 10 to the 23 molecules per mole. Moles will cancel out top and bottom when I multiply. That'll leave me with molecules. And it's 3.43 times 10 to the 23rd molecules. Still not there. I have this. It wants individual chlorines. So now I look at my molecule and realize, okay, for every one of these molecules, I have 4 chlorines. So if I have 1 molecule, I have 4 chlorines. If I have 10 molecules, I have 40 chlorines, right? So that's what this last step is. It's how many chlorine ions are in each molecule. So I take my molecules, 3.43 times 10 to the 23 molecules, and I multiply it by 4 chloride ions per molecule. Molecules on top and on bottom cancel when I multiply, and it's 4 times this number. Common mistake, people go 4 times 3 point something, I'll get like an answer of 12 or so here. They forget this, right? That 10 to the 23 is still there. So when I do multiply that, I end up with this. And this is my final answer. All right, so 1.37 times 10 to the 24 chloride ions. So that's number 5. If you want, take a snapshot of that, and or pause the video, and I'll do another one. All right. Number 6. Number 6, I only put a couple of percent composition ones on this review. I figured if you did it twice, you probably would know how to do it. It's probably one of the easier calculations. I will do the second one. All right? So CaClO3, 2, calcium chlorate. All right? I'm not sure if I gave you the formula or not. You still got to know your names and formulas. That's the number 1 skill. Number 1 most important thing. So if I just gave you the word calcium chlorate, you have to know that this is the formula. And so when I look at that, I have 1 calcium, I have 2 chlorines, even though I drew it kind of messy, and I have 2 times 3, which is 6 oxygens. All right, now I'm using my periodic table and I'm using those atomic masses. So 1 chlorine is 40.08 grams. So 1 calcium is 40.08 grams. 2 chlorines, 7090, that's 35.45 times 2. And then each oxygen is 16 times 6, that's 96. So I always find my 3 individuals first, and then I add these 3 numbers to get my total. And the total when I add those 3 is 206 98. And then I just go down, put 206.98 underneath of each one. And then, of course, because it's a percent, I got to multiply it by 100%. Some people forgot to show this percent sign, right? If my answer is going to be in a percent, then percent has to be over here somewhere. It just can't appear over here and not be in here somewhere. So don't forget these percent signs. So when I do that really quickly, this is 19. These grams all cancel. Grams divided by grams is no grams. So I'll just be left with the percents. This one is 19.36%, 34.25%, and 46.38%. And if I add those up very quickly, I end up with 46, 70, 80, 99, and we'll say that that's the last one to make it 100. So we are good with that. All right, no worries. All right, so that's number 6. That was B. Get that down right now if you haven't already, or pause the video. I'm going to move on to the next one. We're rolling here quickly. Hopefully this stuff here, as I'm going through, you're going like, oh yeah, I remember that. Yeah, that's easy. I got that. Hopefully, that's the goal. Let's do number 9. All right. Number 9. Number 9 was a hydrated salt, and it said you had Na2CO3, sodium carbonate, and it was a hydrated salt. Now, it did not tell us this number right here. We have to figure out what that X is. Remember, with the hydrated salt, you're trying to find the molar ratio, between the salt and the water. And the salt, the sodium carbonate here, is always a 1. This thing's always a 1. This is always the one that's going to change. It could be a 2, a 4, 6, whatever, right? But this is always a 1 in front of here. So you're finding the mole ratio between the salt and the water here. Anyway, and it says the hydrated salt was 250 grams. We heated it up, and all we had left over was the salt. All the water evaporated into the air. So the anhydrous, or dry form of the salt without the water, weighed 92.5 grams. So we have the mass of this, and we have the mass of this and this together. So now we can get the mass of water. So therefore, right, the water we get by taking this number and subtracting this number. This is the salt and water. This is just the salt. If I subtract it, I'll get the water. And when I subtracted those two, it was 157.5 grams. All right. So now I'm going to divide by the molar masses. Formulas are based on amounts, and in chemistry, amounts means moles, right? I've said that a number of times. So amounts means moles. To get to moles, I have to divide by the molar mass, right? So I'm dividing by the molar mass, and this one ends up being 0.873 moles. And this one I divide by water, which is 18.02 grams per mole. And this one ends up being 8.74 moles. I can already see now, that's probably going to be a 1 to 10 here, right? This is 10 times greater than that. So I had to get my masses. I changed them into moles by dividing by the molar mass. There's a molar mass of water. There's a molar mass of the sodium carbonate. I have them in both in moles. The next thing I have to do is divide by the lowest mole number. Well, that's the one that starts with 0. This one starts with 8. 873 moles, 0.873 moles. When I divide that one out, I get a 1. And when I divide this one out, I get a 10. And the moles, they all cancel out. Moles divided by moles is no moles. So therefore, my formula is Na2CO3 I put that little dot there to show that the water is in there but not locked into that. It can easily be evaporated off. So it's sodium carbonate decahydrate. All right, so we had to find this right here. That was our X from above, or from before, sorry. All right, so again, get your masses, turn them into moles. We did that right here by dividing by the molar mass. So there's our moles, and then divide by the lowest mole number, and that should be your ratio. And we said the salt's always 1, and this water in this case was 10. The water is the variable coefficient of sorts here. All right, pause the video if you need to. Get that down, take a look at it. I am going to go on to the next question. All right, next question. Let's give number 12 a try. Number 12 is going to be a tough one to get in here. There's a lot of steps to number 12, but we'll give it a go. 12 is a hydrocarbon. A hydrocarbon just has hydrogen and carbon. And what we are trying to find is what these two numbers are. I just put X and Y in there like math. They're variables. I'm not sure what they are. So I put them in there, and it says, this hydrocarbon, the sample, it's unknown. We don't know these two numbers. They run it through a carbon-hydrogen analyzer. And they find out that carbon dioxide, in that chamber, it weighed 174.69 grams. And the water, it was 95.31 grams. All right? And what it wants the molecular formula of this. All right, so we look at steps for this one. What we have to do is go, we've got our masses, we're going to change them into moles by dividing by the molar mass, and then I'll have moles of carbon dioxide and moles of water. I'll have to convert those into moles of carbon and moles of hydrogen, and there's a little trick to do that. And then of course we divide by the lowest mole number. So let's do that. Let's get the molar masses for these two things in. This one's 44.01. Water's 18.01. You're probably remembering some of these now, just from practice. So divide that out, and this is 3.97 moles of H2O. Or sorry, not H2O. That's the wrong line. CO2. H2O is this line. Hashtag stupid sir. Moles of water. Now, I can't divide by the lowest mole number yet because I don't have carbon and hydrogen. I have carbon dioxide and water. So I have to do that intermediate step. So this step that I'm about to do in the blue, you only do for the hydrocarbon problems, the combustion chamber problems. All right? Every other one, we'd pretty much be dividing by the lowest mole number right now. But there's this extra step. So we got to go from CO2 to C and H2O to H. And how we do that is we take these values. So I'll do the carbon here. And we multiply it by the number of carbon. So 1 mole of carbon for every mole of CO2. Every CO2 has 1 carbon. So the number doesn't change. But now I have moles of carbon because moles of carbon dioxide on top and on bottom will cancel when I multiply. And because there's only 1 carbon in it, that number stays the same. That's the easy one. So moles of carbon. Water, 5.29 moles of H2O times. Now look at water. It has 2 H's for every H2O. So 2 moles of H for every mole of H2O. I multiply that and I get 10.58 moles of hydrogen. Now I have my individual elements. Now I can divide by the molar mass. So go back to the black marker here, the regular one. So this blue step here, that's one that we do only for the hydrocarbon analysis. All right, the combustion chamber problems. So when I divide this out by the lower mole number, well, that's the 3 versus the 10. So 3.97 moles. 3.97 moles. I end up with, well, this one's obviously 1. And this one's 2.66. And that's a problem. Right? A lot of the times when we did this, we'll get 1 and a 2 or a 3 or a nice round number. Here we've got this. That's a problem. So what do we do when we have 0.67? When that's basically what this is, we multiply by 3. Remember, if one of them ends in 0.5, we multiply by 2. If it ends in 0.33 or 0.67, we multiply those by 3. All right? So we have this one right here. So we're going to multiply these both by 3. And you don't just multiply this one by 3, it's both of them. So even though one is nice and even as it is, or nice and round, we still have to do that. So our empirical formula, the empirical formula is C3H8. All right, we got these two numbers right here. It wanted the molecular formula. All right, now in this problem, it told me that the molar mass for the unknown, when they used the mass spectrometer, was 44.17 grams per mole. So the real, the real live molecule, the molecular one, had this molar mass. We'll use that now, all right? I'm going to need more space on the board here, so what I'm going to do is, actually maybe I'll try to squeeze it in. This could end up being a disaster. I'll try to squeeze it down here with the pink marker here. So what I'm going to do is take that molar mass that was given. I'm going to divide it. I'm going to divide it by the empirical formula mass. Now the molar mass was given. It's 4417 grams per mole. And my empirical formula mass I get from this. So using the periodic table, 3 carbons, 8 hydrogens, add that together, and it's 44.11 grams per mole. And that's 1. These will cancel. That's 1. Close enough. So what that means is that my molecular formula is 1. I take this 1, and I multiply it by C3H8, so it stays the same. So my molecular formula is the same as my empirical formula. Sometimes that happens, right? Sometimes the real formula is already in lowest terms. If this is a molecular formula, that means this is propane, the same stuff that's in your barbecue tanks. All right? So that's number 12. I was able to squeeze it all onto one board. All right? The next one that we will give a try to. Let's try let's do number 11. All right, we'll do number 11. I know I just did number 12. I'll do number 11. Pause the screen if you need to take a look at this. Pause it. Look at your notes. I'm going to do number 11. We're working a little bit backwards here, but who cares? We'll do what we want. That's what chemists do, right? All right. Number 11. Number 11 says an oxide of aluminum, and again, we don't know what these numbers are. There's an X and a Y here. An oxide of aluminum was 150 grams. They heat it up. The oxygen goes into the air. The metal residue, the aluminum in this case, left behind. The metal residue has a mass of 79.35 grams. I can figure out my oxygen. My oxygen would be, well, this is the Al and the O together. This is the Al, so if I take this and subtract this, I'll get the O. When I do that, it's 70.65 grams of oxygen. First step, get the masses. The next step is to turn them into moles. So I divide by the molar mass off of the periodic table. And oxygen is 16 grams per mole. You're probably remembering a lot of the molar masses by now as well. And when I do that, I get 2.94 moles of aluminum, and I get 4.415 moles of oxygen. Now, for rounding off, some people ask me when I round off, you know, would 4.4 or 2.9 work? I always like to go a little bit after the decimal, and I had 4.15, and then like maybe it was a 0 or something. I kept the 5, right? We aren't doing significant digits right now. We will do them at the end. I'll run a few days course on significant digits, so you know how to do them for grade 12. But with the pandemic thing going on, I just wanted us to make sure we knew the chemistry theory and how to do it first. Sig digs you can learn down the line pretty easily if you put a little time into them. So I have the molar amounts for each element. I'm going to divide by the lowest mole number. So that's the 2.94, and they both get divided by that. This one obviously is 1. Moles divided by moles will cancel. And this one is 1.5. So again, this is a problem. It's not a nice, neat number. I can't have a formula of Al1, O 1.5. So remember, with 0.5, what we do is we double it. But if we double one, we double the other. So this becomes 2, and this becomes 3. And those are my numbers in my formula. So therefore, the formula is Al2O3. Aluminum oxide, and that's my answer right there. All right. Pretty straightforward stuff. We'll do 2 more. All right. Forgot to say pause the video, but I think you guys know how YouTube works by now. You can go back and pause it if you need. All right, let's do 16. 16. Number 16 gives us percent composition of an element, of a compound that has C, H, and O. So it gives us the percent composition. Remember, when we're given percent composition, what we do is we immediately take that percent from the percent composition and turn it immediately into grams. We assume 100 grams. And then we turn the grams into moles, and then we use the lowest mole, right? And then we get our formula. So they gave us percentages, percent composition by mass, and so now we're going to use those. So 63.2% becomes, whoa, I wrote the percent again. It becomes grams. Oxygen, 5.26% becomes grams, and the 31.60 of oxygen becomes grams. These 3 numbers should add up to 100 or pretty darn close, depending on the rounding. The next thing I'm going to do is I'm going to divide by the molar mass to get the moles. Formulas are based on amounts. Amounts in chemistry is moles. They're not based on grams. So I got to turn the grams into moles. So the periodic table, carbon is 12.01, hydrogen 1.01, oxygen 16, and that's all grams per mole. All right. When I divide those, I get 5.26 moles for this, 5.21 moles for that, and 1.975 moles for this. All right. I'm going to erase this because I'm going to need this space. All right. I've got my moles. Now I'm going to divide by the lowest mole number. And the lowest mole number here is 1.9. Right? I got 5 and 5. 1 is way below those. So I divide each one by 1.975 moles. 1.975 moles. Moles divided by moles will cancel. Someone asked, do I have to do this? Do I have to show that? No, you don't have to. I will understand that moles divided by moles. You don't have to do these slashes. I do them just to show you guys that they cancel. Right? I didn't do it with the grams here, but we didn't have grams in our answer. So it's understood that the grams cancel. This one is 1. And this one is 2.66 and 2.64. We've seen this before, right? These two right here are going to be a problem, but they're basically 0.67, right? A little bit of rounding. They weren't exactly 2.67, but I know what I have to do. I have to multiply each of these by 3. When I have a 0.67 or a 0.66 or a 0.33, I multiply by 3. And that makes this into 3, and it makes these ones into 8s. So therefore, the empirical formula is C8H8O3. All right, and that is the correct answer. So that's number 16. I will do one more. I'll do number 17. Now remember, on this review, for the first quest tomorrow, it's 1 to 17. Be able to do that stuff. Number 18 is the start of stoichiometry. That is the one that is after this. All right? So 1 to 17 is for the quest tomorrow. I'm going to erase this. Pause the video if you need to. I'm going to do number 17, then we'll call it a night, because it's late enough as it is. So, 17. Now, 17 has carbon, hydrogen, and oxygen, but it doesn't give us percent composition. It gives us a breakdown of a mass of it, so we're already in masses. So I always start with the masses, and that's fine. What did we do if we were given percent composition? We turned it into mass anyway. So this one just gives us the mass right off the get-go. So we write the masses down. And then what we're going to do is turn the mass into moles, because formulas are based on moles, not mass. So I use the values off the periodic table, and I divide them by each element's molar mass, which is the same as the atomic mass on that periodic table. When I do that, I get 0.263 moles of this, 0.263 moles of that, and 0.0657 moles of this. What this tells me is that in my formula, these two, carbon and hydrogen, are going to have the same number. All right? They have the same molar amount, which means C and H are going to have the same number. My lowest one is right here, right? There's a 0 here after the decimal. There isn't one here or here, so this is my lowest number. And I'm going to divide every one of them by that. .0657 moles. Make sure to show your units. Oh my God. I had to take off marks off of smart people that knew what they were doing, but they didn't show their units. And it's just like math. It's just like physics. Right? I know Mr. O'Meara, Miss Burke, I know your math teachers, Miss Chang. If you're not showing units or your work, you lose marks. So show the units. Keep your marks. I don't want them. You keep them. You need them, right? So look after yourself. Moles divided by moles will cancel. I'm not going to cross all those out. You understand. These ones end up being 4. Nice and easy. So your empirical formula for this last one is C4H4. We said those two would be the same, and O. And that is the correct answer. God, I'm really good at chem. Anyway, hopefully you're as good as me tomorrow and can ace this chem quest. If there's any comments or concerns, please comment on the video. Comment on the video in the comment section below this video on YouTube, or get a hold of me through Edsby if you're one of my students. My brain is tired. That's a lot of work. It's been a long day. Anyway, keep your energy up. Keep battling. If you need any help, please ask. You can't sit there and not know. All right? Hope everything is crystal clear. We'll see you tomorrow. Bye-bye.